I'm sharing my screen. Let me know once it is visible. Can anyone can turn on your mic and confirm? Hello? Can anyone confirm whether my screen is visible?
Yes, sir, we can see you speak.
Okay, good. So I will continue with the short circuit studies. So the single line, first we need to build the single line diagram. So it is similar to our load flow analysis. So first of all, we would like to first do the settings. So I will select with IEC and 50 Hz frequency. So just I built the two bus system. So I will explain you how we can do that. So what are the data required for the load flow analysis? So those details we need to enter it first. So I entered the ID, bus voltage, then transformer in the rating page, transformer MVA, then transformer impedance. So those things I selected. Then in addition to that, in the grid, so we need to update the grid short circuit capacity. So it means whenever there is a fault, what is the maximum fault current grid can contribute. So that normally will be in MVA or MVA, or sometime it will be in kilo ampere. So just now I'm just considering 1000 MVA as a grid fault current, and XPR ratio is 14. So it's some atypical value. Okay, so once we modeled the single line diagram, so for doing the short circuit study, so we have to go to the short circuit page. In the short circuit page, so we have to go for the study case. This suitcase symbol is the edit study case. So in this edit study case, we have to just select what standard we are going to apply for the fault. So first we need to select the standard, then C factor. In IEC there is a factor called C factor, so we need to select the C factor. So maximum C factor we are going to consider, or minimum one, or user defined three option is there. So the value what they have entered here, so this is as per IEC 60909 standard. So based on that standard we have to consider the C factor. So the C factor is used for the short circuit current calculation. So those things we need to update. Then calculation method, here method A, B, C is there, so mostly we will use method C for the fault current contribution. So these things we need to select it, and After that, we can go for the short circuit study. So in the right side there is duty. So run three-phase device duty, then uh, run panel single phase UPS single phase system. Then the next one is the IEC 60909 fault current. Then next one will be IEC 61363. So this standard normally we are not using. This standard I think used for 400 hertz frequency system. So mostly used in SIPs. Okay, so here in a practical power system, electrical fault can happen anywhere in the power system, in the transmission line or in the bus, and also the equipment. So whether it can the fault can happen internally to the equipment also or outside the equipment also. But in the software, mostly in this ETAP, so we can have the fault mostly in the bus only. So if you select the bus, right click, then make it fault. So what are the bus we want to calculate the fault current? So those buses we can select it. So by one we can select it through like this. Or one more option is there in the edit study case. So in the info page, so here the left side is a bus selection faulted bus. So what are the bus we are going to do, going to calculate the fault current. In the right hand side, don't fault. So we at presently we don't have, we have two buses, so bus 3 and 4. So we can just select these buses, and if we press this fault means it will go to the bus selection page. Suppose if 100 buses is there, so by doing it one by one it will take more time. So in this way we can easily select the number of buses for the fault studies. So now I selected the two buses. Okay, so just run IEC 60909. No bus is faulted. Okay, so I will tell you how to see that result. Okay, so here uh, we are getting multiple values. So the first one is the voltage. So presently this bus 3 voltage is at the time of fault is 0 kV and voltage angle is 0. For the bus 4 also, the voltage is 0 kV and voltage angle also 0. So it means it is a uh, 0 voltage fault. So it is zero impedance fault. So normally we will call as bolded fault. Okay. So from the grid, so we are getting 17.495 kilo ampere as a fault current during the fault. So in the bus, so we are getting 17.495 kilo ampere at this bus. So in the low voltage side, in 11 kV side, so due to the transformer impedance, the fault current at the low voltage bus has been reduced. So it is 6.135 kilo ampere. So in the bus also it is 6.135 kilo ampere. So as we know, we have different type of fault: three-phase fault, single line to ground fault, double line to ground fault, and line to line fault. So what fault current it is, we can check it through this Y symbol display option. So presently it is three-phase fault. Suppose if you want to single line to ground fault, so we have to go with a single line to ground fault, and we can see the single line to ground fault value here. So for the line to line, then LLG. Okay, so most of the places we need to check all the type of faults for any selection of the circuit breaker. So we need to check all the fault current only. So but in most of the cases, the three-phase fault current normally higher than all other type of fault current. So suppose in most of the cases, the three-phase fault current magnitude value is high. Suppose if you are calculating the three-phase magnitude fault current, so that value, it's high, so other values are less. So the three-phase fault current is considered for the circuit breaker or other equipment selections. So in this single line diagram, we just seen that the fault current study, how we can do it for the typical two bus system. So now again, I will introduce a few other buses. So here I will introduce one cable. I'm again connecting the same static type of load. So just I'm taking cable length as 1 kilometer. Just going to select the cable library from this. I just selected that. So now I am making this bus also fault. I am running that IEC 60909. Can you able to see in this bus 4 the fault magnitude is 6.135 kiloampere, but in bus 5 it is 5.524 kiloampere. So the fault current magnitude is reduced because of the impedance offered by the cable. Okay, so the in the cable select in the cable selection also, um, there are some requirements are there. So how to select the cable? So so for the cable selection, there are multiple criteria is there. So one of the criteria is fault current. So A equal to I into root T divided by K. So A means square size of the cable. A is size of the cable. So this is for the short circuit current calculation. So I is fault current. I is fault current. T, this T is time, that is breaker operating time. Then K is constant. So for K, I remember 146 for aluminum cable, and 220 for copper cable, I remember. So based on this formula, so we have to arrive this size. Okay, so the cable what we are going to use it this location, so we have to select based on this formula. So in the particular cable type of feeder, here one circuit breaker will be there. In this location also one circuit breaker will be there. This is will be circuit breaker 1, and this will be circuit breaker 2. So 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 this CB, this time t is there, no? This time t belongs to this CB1. So in what time this CB1 will operate, so that time we have to consider. So based on this one, so this I is there, no, this I is this fault current 6.135. Okay, so if it is aluminum cable 146 and copper cable 220, so I is the fault current, time t is the circuit breaker operating so time. So normally it will be 0 0.4 second or 0 0.6 seconds, so based on the coordination curve, so this time depends. So based on that we have to calculate so the minimum size. So what is the size square area is coming? So the selected cable in this location has to be equal to this size or higher size, so that the particular cable can withstand this fault current. Okay, so I hope you are all understand this, how this the cable selection has been done. So several criteria is there. So one of the criteria is the cable has to withstand the fault current flowing through it. So this is the formula: A equal to I into root T divided by K. So this is the formula. So A is the size, I is the fault current in ampere, T is the breaker operating time, K is the constant for the cable material. I hope you are clear. So the impedance offered by the cable will limit some fault current. Okay, so because of that reason, the fault current magnitude at this bus location is lesser compared to this bus. Okay, so I will introduce now one more case. Okay, so I'm just going to copy paste the same cable. Okay, copy paste the same cable. All the properties of this cable and this cable is remain same. Can able to see the difference? Here it is cable 1, but when I copy and paste it, it become cable 3. So in between one cable is there, but unfortunately that cable is there in this system dumpster. Here cable is there. The moment we copy, so the copied file will come to this dumpster. So we have to clean it. Suppose if we need to take any value from any element from the dumpster means, so we have to move it from dumpster. In place of putting paste, if we move it from dumpster means the particular element will move from dumpster to here, so the number will be in continue with that. So I will introduce one induction motor. So I will just put 1000 kilowatt induction motor. Okay, again I am going to the short circuit page, making the bus as a fault. Then I am running the device duty. Okay, so now I will tell you one more factor is there. Now I will tell you. Okay, so here can able to see in this bus can able to see, so the maximum fault current, that is 5.865 is coming from the grid source to this fault point bus 5. But in this bus, that is bus number 6, 5.524 kilo ampere fault current is coming from this grid source to the fault point, and 0.433 kilo ampere of fault current is contributed by this induction motor. Because the induction motor having the inertia, so at the time of fault, induction the motor will deliver some amount of fault current. Yeah, right. So that's what I explained in the last session. So in the conventional electrical machine, including generators, motor having the inertia, so at the time of fault, it will contribute some amount of fault current to the fault point. But in the modern inverter based system, so in a solar plant or wind plant, etc., so those elements doesn't have this um, rotating part, that is inertia. So if any fault happen, those elements will not contribute any fault current to this faulted point. So I hope everyone is clear with that. If you have any doubt as of now, then yeah, you can please turn on your mic and you can ask me some questions. Okay, if there is no question, then I will continue further. Okay, so let's assume the circuit breaker used in this location is 5 kiloampere. Okay, so the present short circuit current is 5.865 kiloampere. So it means the circuit breaker CB rating is 5 kiloampere. Then available fault current is 5.86. Okay, so the whether this circuit breaker rating is accepted? No. So when we are comparing the fault current, the circuit breaker rating shall be above the fault current. So here the circuit breaker rating, the minimum rating of the circuit breaker has to be 5.86 or above. Okay, but in this location, compared to the circuit breaker rating, this fault current rating is high. So we don't have much option. Then we have to, what is that, we have to reduce first option. What we have is that increase the rating of the circuit breaker to the 5.86 or higher value. So that is the option 1, that is uh, increase circuit breaker rating. Second option, uh, reduce the fault current. Okay, so first option, we have to increase the circuit breaker rating, or second option, we have to reduce the fault current. So in place of 5 kiloampere, we can go to the higher size rating, that is the option 1. Suppose if that option is not feasible, then alternatively what we can do, suppose if the project is in planning stage, we can increase some smaller impedance in this cable. Okay, so if the impedance is increasing means, then definitely it will reduce some amount of fault current. So if the length is increasing means, then cable impedance also increases. So in place of 1 kiloampere 1 kilometer length, just I'm changing it to 1.2 kilometer change, 1.2 kilometer length. So presently it is 5.865 kiloampere. After changing, it will change. Now it is 5.732. So the fault current reduction, small amount of reduction is happened, but not that much. So in order to reduce the fault current further, we have some other option. There are multiple option is there. So one of the option is to increase some amount of impedance in the transformer. Presently it is in 8.35. So for just one calculation purpose, I'm going to increase it to 9.35. So presently the fault current is 5.737 with 8.35 percentage impedance. After changing the impedance to 9.35 percentage, it become 5.308. Okay, so still the fault current is in higher value. So for that, what we can do, so there are some reactor is there, that is fault current limiting reactor. So normally those reactors, normally we will, what we will do here, reactor is there, no? So this reactor, so this reactor normally we will add as a series reactor to the bus. So we will connect in between the bus. So we have to select how much current we are limiting through this reactor, then the reactor will limit the fault current. So this reactor is called um, fault limiting reactor. This also one of the methodology to one of the methodology to reduce the fault current. So the first one what we have, so totally how to manage the situation, one is increase the circuit breaker rating. So that is the first option. In the second option we have to reduce the fault current. So the fault current we can reduce it in multiple way. So the one option is increase the cable impedance by increasing the cable length. That is one option. The second option, increase the transformer impedance. That is one option. In other option is that introducing the what is that fault current limiting reactor. So this also we can we can do it to reduce the fault current. Okay, so have everyone understand as of now? So just I am giving some basics of the fault currents only. So other the mostly my suggestion is that you have to practice it. So you have to refer the theoretical guidelines, and then you have to check whether it is working or not in the software, whether the theoretical concept is working or not. So that part you have to do it. So regularly I'm suggesting you to continue or practice for almost 15 to 20 minutes per day, so that you will become more familiarized with the software as well as the concept how you can use it. Okay, so so if you have any other, if you do you have any doubts in the short circuit current calculation? If you don't have any doubt, then we will move to the harmonic analysis. So again, I am going to open IEEE 399. So in ETAP, this symbol, this harmonic symbol. Oh, 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 oh. Unfortunately, this harmonic analysis is not having the feature in this demo version. Okay, no problem. I will tell you how to do that. So if you, in your university, if you have the uh, license, original license, you can practice it. Harmonic analysis. So the chapter 10 is the harmonic analysis. So theoretical information is available here. So I will directly go to how to do that. Okay, this 10.5.9. So how to do the harmonic analysis? So they have given the step-by-step procedure. So the first one is the preparation of single line diagram. Suppose if you are going to do any harmonic analysis, the first step is to get the single line diagram. Okay, so in the single line diagram, the single line diagram has the latest addition deletion in of the system. Uh, so in simple words, the single line diagram is the updated one. So in that all the network elements are included for the particular system. Okay, then second one is the rating of the each and every equipments in the single line diagram. Then third one is the non-linear loads in the system. So before going into this one, I will tell you what is harmonics. So as we are all know, our power system frequency is 50 hertz or 60 hertz based on the country to country. So for an example, if it is 50 hertz frequency, then the power system parameters such as voltage and current frequency also 50 hertz. Okay, so whenever there is a non-linear load, so non-linear load means in simple definition, suppose if I am connecting any load to the source, that is source, so that time due to the non-linear characteristics of the particular load, even though if we provide the sinusoidal voltage, the load will draw the non-sinusoidal current. So those loads are called as non-linear loads. So those non-linear loads are mostly made up of power electronic based converters like converters, rectifiers, chargers, VFDs, solar inverters or wind turbine generators, cycloconverter. Then other non-linear loads electric arc furnace. Okay, so these are all some of the equipments non-linear loads normally we will use it in the power system. Okay, so these equipment will introduce the non-linear characteristics into the system. So these non-linear characteristics are called as harmonics. So these harmonics will introduce many more frequency into the fundamental frequency of 50 hertz or 60 hertz. Those frequencies are called as non-linear frequencies. So what is the significance of harmonics, why harmonic is important, what is the effect of the harmonics? All the theoretical information is available in this standard, so you can go through it, and if you have any doubt you can directly contact through me through mobile, WhatsApp or email. So I am happy to reply back to you. So the presently in the modern power system, the use of power electronic based converters is increased, starting from the power generation from large scale solar plant, large scale wind plant to the small scale laptop charger, mobile charger, etc. are made up of power electronic based converters. So it increasing the harmonics into the power system. So that's the reason the harmonics is plays an important role in this modern power system, right? So in a single line diagram where and all the non-linear loads is coming, okay, then what are the non-linear current the particular load can generate, those information also. Suppose if 10 non-linear load is there, all the 10 non-linear loads are different rating means, so we have to get the harmonic generation, current generation by all the 10 loads, we have to get it. So what are the harmonic frequency it can generate, and then what is its magnitude and phase angle. So these information we have to get it from the particular non-linear load manufacturer. Suppose if it is VFD manufactured by Siemens means we have to get it from Siemens. Suppose if it is from ABB, then we have to get it from ABB, right? Okay, then next one is the obtain relevant utility information harmonic data. So we seen the single line diagram like this. So here the grid is the power source. So utility means grid only. So the grid also having some harmonics and the voltage. So we have to get the grid capacity, that is the harmonics voltage, that is technically called as background harmonic voltage. Those background harmonic voltage we have to get it, and what is their short circuit strength, those information we have to get it. Okay, so suppose if this particular load is harmonic producing load means, for this load we have to get the harmonic generation current data. So here the harmonic page will be there. So in the harmonic page I will open one value. So here one ABB VFD current source is there. So here can able to see so here the harmonic magnet. So for by this particular VFT will produce this much harmonic spectrum at the time of uh, operation, right? Then this is the as I told, this is the short circuit uh, uh, of the grid. So we have to get it, and the background harmonic voltage, then how much amount of distortion we have to maintain at this particular location. So normally we have to comply the harmonics limit at PCC. PCC means point of common coupling. So that is the interface point between the utility company and the industrial company. So the interconnection point is called as PCC. Generally, this PCC point is the billing point where the utility or discom or transmission company is charging the particular industrial company for the energy consumption. So for that location, we have to maintain it. Then carry out the harmonic analysis for the base system configuration. So base system configuration means here it is a simple system. So here only one configuration only. In a large system, two power grid sources will be there, multiple transformer will be there, multiple generator will be there, and last session we see no bus coupler or tie breaker. So switching on the tie breaker, switching off the tie breaker, so like that we have to do the harmonic analysis in multiple times. So from the so after running the harmonic analysis, so we have to calculate the total harmonic distortion and individual harmonic distortion, it is within the limit or not. So that limit we have to, so the calculated value we need to check with the value provided by the utility whether it is acceptable or not. If acceptable, then it is fine. If it is not acceptable, then again we have to come this location from the single line diagram. If suppose if fifth order harmonic is exceeding means, then we have to mitigate the particular fifth order harmonic by introducing the harmonic filter. So we have to filter out the harmonic magnitude. Okay, so we have to filter out the harmonic magnitude. Then after that, again we have to run the calculation, and we have to come to this particular step, and we have to check the present harmonic magnitude is within the limit or not. If it is within the limit, then it is fine. If it is not fine, then again we have to go to the same step. Then we have to increase the rating, or we have to provide some additional filters, and we have to check it. Okay, so this is the additional filter. Okay, good. So these are all the step by step procedure for the how to perform the harmonic analysis. Okay, so I have written one book. So in that book, I have given the explanation in clear. So I will share the particular book details to you. If you have the book access in your university, then you can go through that. Suppose suppose in the later stage, suppose if you are getting any doubt with respect to this how to use the software, or any particular doubt on any technical concept, etc., you don't hesitate, you reach out to me through WhatsApp or email. I am happy to support you. Okay, so if you have any doubt, then you can please ask me. Okay, then I will go to one by one. I'm just stop sharing my screen. So anyone have any questions? Anyone have any questions? Okay, good. So now we came to the end of today's session and end of this training program. We will share the recordings with everyone. Then you can access it whenever you required it. Okay, so thank you all. Thanks everyone for attending this IEEE PES YP, the first session on the software training on ETAP. So when we planned to start this session, so our intention is to introduce some technical things, or some job oriented software or skill into the students, so that after completing their graduation or post graduation, so they can able to meet, or they can able to get some industrial oriented job, especially as an power system engineer, or power system specialist, or power system analyst. Okay, so that is our intention to introduce this course. So this is the first course. So in this course, the power system analysis is a vast topic. So in this course, I just covered only the load flow and short circuit analysis. But I thought to cover the harmonic analysis also. But unfortunately, due to the limited feature in the ETAP demo version for the harmonic analysis, so I could not able to give the demonstration on harmonic analysis, how it will work, so how we can explore it. But unfortunately, at this moment it's not possible. Suppose in if your laboratory, or if your university having these softwares, then you can practice it. So my suggestion, practice it regularly for 20 minutes to 30 minutes every day, so that you will become familiar in this technical concept as well as the technical software. For the power system engineer across the globe, we have good opportunity, especially for the power system studies. So doing the load flow, short circuit, transient, harmonic, motor starting, air class, dynamic studies, stability studies, etc. across the globe. So we are having the opening. So as a power system engineer, we have the requirement across the globe. So I'm requesting or insisting everyone to practice the technical concept and software. So ETAB is just one of the software. And at the first session I told you, right? Normally we have two type of calculations. The first one is the RMS based calculation. Second one is the EMT based calculation. ETAB and Excel and Power Factory PSSC are all RMS based calculation tool. EMTPRV and PSCADs are the instantaneous based tools, that is EMT based tools. Okay, right? So we just seen this ETAB only in this session. So if after completing or after practicing this, so you have to go for the one of the EMT based studies. So if you have the working knowledge of any one of the RMS based tool and any one of the EMT based tool, that will add an advantage to your profile. Okay, so oh, I'm happy to interact with you everyone. uh, Thank you for your mm, wonderful time. So, okay, so